Hello everyone. This is a discussion about Chapter 17 and the homework, and I put together some sample data to help you understand, give you some guidance on how to complete homework problem 6 on page 586. So we have some information given to us from the problem. We have an item cost of $15. We have an order cost of $200. Our holding cost in this case is 25% of the item cost. I've done that calculation for you now, and it's $3.75. Our average demand is 30,000 units. I'm sorry, an annual demand of 30,000 units. Our average demand is 600, and that's calculated by our annual demand divided by a 50-week demand cycle, or 600 per week. That demand has over time been studied, and we have a standard deviation of demand of 30 units. The lead time from our supplier on parts we buy is 2 weeks, and we want to have a service level of 95% for our customers, meaning that 95% of the time, if a customer comes in, statistically we want to be able to serve them without an out of stock. Or said another way, we're okay with being out of stock 5% of the time. So the questions are broken into 3 parts. First, calculating the order quantity and the reorder point, pretty straightforward, and determining what those handling or holding costs will be, as well as order costs. And then we throw in a little twist that we haven't talked about yet in class, and that's if we're able to get a price break from our supplier, should we take it? All right, well, let's get started looking at part A, which is determining our order quantity and reorder point. So we know from discussions that our quantity for ordering, or our Q optimum, is equal to the square root of 2 times our annual demand times our order costs, and that's divided by our holding costs. Straight from the book. So let's use Excel to calculate that. Using the square root function, we're going to take 2 times our annual demand, 30,000 units, times our cost per order of $200, divided by our holding cost of $3.75 per unit. And that comes back with an order quantity to optimize or minimize costs of 1,788.85 units. And I'm going to round that so we can use a round number with no decimals. I want to round that to 1789. So every time we place an order, given the costs that we have and our annual demand, we will minimize ordering and holding costs if we order 1,789 units. And it also asks us to calculate our reorder point, which we know is our average demand times our lead time. And then if we have safety stock, we're going to add to that our Z value times our standard deviation. And let's look at our average demand and lead time, and then we'll add the safety stock to it. Our average demand is 600 units per week, and we have a lead time of 2 weeks. So without safety stock, this would be our reorder point. But because we have said we want to have a 95% service level, let's figure out what that extra safety stock will be. It's our Z value. And that Z value we said was calculated either by looking at the back of the book or by using the norms INV function and putting in our probability. In this case, we want 95%. So this is our Z value for a 95% service level. If you look in the back of the book, that number is about 1.65. we're going to use 1.644 for our calculation. So that means our safety stock is going to be that number times our standard deviation. So we're going to carry a safety stock of 49.3456 units. I'm going to round that again and say that we carry a safety stock of 49 units. So the total amount of our reorder point is going to be the 1200, which is our lead time, times our average demand plus our safety stock. So this is our reorder point with safety stock. Okay, pretty straightforward so far. No surprises. So based on that, we know we're going to have a cost to order and a cost to hold the inventory. Let's look at our holding cost first. Our holding cost is simply our average inventory, which is Q over 2. But because we have a safety stock, we have to add that safety stock in there. And then we're going to take that whole quantity times our holding cost. And it didn't like that because I spelled it out. But it's our average inventory plus our safety stock. And just to make sure we do the math right, that's all multiplied by our holding cost. So in this case, our Q is 1789 divided by 2 plus our safety stock we calculated at 49 units. That's how many units are subject to the holding cost. And if we multiply that now by our holding cost of $3.75 a unit, we're going to come up with a holding cost of $3,583.15. That is our holding cost annually for ordering 1,789 units, carrying 49 units in safety stock, if it costs us $3.75 to hold inventory. We also have order cost, and that's going to be equal to our annual demand, D, divided by our Q optimum. So basically it's how many we need per year divided by how many we're going to order each time. That tells us how many orders we're going to place. And you multiply that by your order cost. So again, our annual demand, in this case 30,000 units. We're going to order 1,789 units. That means we're going to place 16.77 orders or so per year. And every time we place an order, we have an order cost, which means our total here is $3,354. So if we add the two together, we're going to come up with total annual and ordering costs, holding costs plus ordering costs are going to be equal to $6,891.95. So far, so good. So now we have this little twist where the vendor comes back and says, well, if you order 2,000 units at a time, and I didn't write that in here, but we're going to say we have to order 2,000 units to get a price break. And that price break is $50 per order. The question then is, are we better off to order 2,000 units at the lower ordering cost, or are we better off to order 1,789 units with the given data we have? Because we know the 1,789 with an ordering cost of 200, with a holding cost of 375, with the service probability of 95%, with a 2-week lead time, a 30 unit per week standard deviation, all of that information our costs are minimized when we order 1,789 units, plus we have that desired safety stock. So there's a couple ways to look at this. I'd be curious to know, with that new ordering cost, what our new Q optimum is, because we know ordering costs, which is referred to as S in the book, are part of our Q optimum formula. So let's just run it to see what a $50 savings would generate to minimize cost and see what that number is. So we're going to say square root of 2 times our annual demand times our ordering costs, and in this case they're going to be the $200 we normally pay minus the $50 they've offered in savings, and then we divide that by our holding cost. And it didn't like my formula because I didn't put a parenthesis at the end, but it did it for me, so I forgot the parenthesis on the end. So it says our new Q optimum with a, and I'm going to just, for purposes of keeping it straight, with a $50 savings in ordering cost, is 1,549 units. So we know that we're not going to minimize cost if we order 2,000 units, because to minimize cost we have to order 1,549. But we don't know what it's going to cost yet. It could still save us money, but it may not be optimal. So let's go in and take a look. We know again what our holding costs are going to be. It's going to be our Q optimum divided by 2 plus our safety stock times our holding cost. Now in this case we have a new Q optimum. We have 2,000 now divided by 2, plus we still have a safety stock over here of 49 times our holding cost of 375, and that hasn't changed. 375 is still what it was. We now have a new holding cost of $3,933.75. That's our holding cost. Compare that to $3,538.13, and it makes sense that that number would be higher. Why is that? Because we're now bringing in 2,000 units every time we order, so our average inventory is higher. This holding cost of $35.38 was based on 1,289 units per every order, but we're being forced to order 2,000 to get this price break. So far it's not looking good. Let's see what our order costs change to. So we know our order costs are going to be our annual demand divided by our Q optimum, in this case our new Q optimum, basically the number of orders we place during the year, times our ordering cost. So now we have a annual demand of 30,000, which hasn't changed. We have a new Q optimum of 2,000, which by the way means we're going to order 15 orders during the year. And we have a new order cost. Instead of 200, we're getting a discount of 50. So our ordering costs have gone from $3,353 because we were placing more orders during the year, and it was costing us more per order. That order cost has now dropped to $2,250. So while our holding costs went up, our ordering costs went down. And if we look at our total holding cost plus ordering cost, let's see what they are. Holding cost plus ordering cost are now $6,184. So we had all this math done, everything was going great. We figured 1,789 was our optimum quantity to order, 49 in safety stock, and then the vendor came back and shot us a curve and said, well, we'll give you a discount if you order more than you should. And in this case, by giving us a $50 savings per order, even though we had higher and increased holding costs, our ordering costs dropped by more than we saw of an increase in holding costs, so our total cost